There we go. Okay, so what we've got going today is we're gonna go through the wave function from a really tangible, well, a useful way for the majority of the chemistry that people do. And so to begin with today, the first thing I want to do is just remind you what the wave function is and when does it become useful. And so that's when we think about the physical meaning of a wave function, what that is, right? We're saying, oh, well, the wave function is describing the electron as it moves around the nucleus. But when it comes to the actual description of the electron, we can't know its exact path because of this thing that is the Heisenberg uncertainty principle. And because the electron is a piece of matter that happens to have a wave that is an important wave in its understanding, and we know waves are more delocalized, so it's really hard to get both the position and speed of that electron at the same time. So understanding the exact path of the electron is not useful to us or I mean, it would be useful if we could do it, but we just aren't good at doing that right now. But what we can get out of that is the square of the wave function actually leads to these probability distributions. And the probability distribution of an electron is just saying, where would you expect to find that electron around the nucleus at any given time within 99% of that time. Now, we describe this probability distribution because it's saying essentially where the electrons generally are around an atom, with the caveat that this is for the solution to the wave function. Well, not just the wave function, the wave function can have, there are many possible wave functions, possible solutions to a wave function for an atom. And those solutions to the wave function for the atom give us these somewhat different possible probability distributions. And we call those probability distributions atomic orbitals. It's essentially how is the electron orbiting the nucleus. And we related that to these quantum numbers, right? And so those quantum numbers tell us, given an electron has these quantum numbers to help describe it, right? Those quantum numbers are solutions to the wave functions that lead to these different possible distributions of the electron around the nucleus, depending upon basically things like how much energy does that electron have. And so we have these orbitals, these probability distributions, which tell us where the electrons are. And that's going to be really important for our understanding of the properties of molecules. So it's not necessarily that we really have to know how the math that comes about or that describes all of this, because if you can take what the math gives us, and there's a lot of calculus involved here that's beyond the scope of this class that you would see in a future course if you go on to, say, physical chemistry and you have your calculus and your multivariable calculus. So you can do all kinds of integration and all that kind of stuff. You could do all the math to get these pictures. But for us, where we're at, the pictures are the important thing because the pictures will lead us to a better understanding of how things like bonding works between two atoms. And that's what we're going to really need to dive into now, which is sort of the next step, is taking these orbitals and being able to describe and draw to some extent their shapes. Now, you know how hard it is to draw online, so I'll do my best here at drawing it for you so you can kind of see how some of these artist renderings, right? These are just showing you distributions of those electrons in the probability distribution. Whereas you have an artist rendering, so this is for a p orbital up in the top right. And the artist rendering of a p orbital looks something like this. So it's you're going to see that these artist renderings are much better than what I expect you to be able to do. I'm going to have some really simple two-dimensional versions of what these artists are trying to represent, on a two-dimensional page, but in a way that looks three-dimensional. So I'm not expecting you to be a fantastic artist. I'm not. But I would like you, and you do need to know how to draw these orbitals, at least from a two-dimensional standpoint. And so that's part of what we're doing today. And we're also going to relate the shapes and sizes of these orbitals and their orientations in space to these quantum numbers, right? And so we had these quantum numbers we went over. We had the principal quantum number, right? So the principal quantum number tells you how big an orbital is. The smaller the value, the smaller the orbital, the closer to the nucleus it is. The angular momentum quantum number describes the shape of an orbital. So if it's an s orbital, it's going to be spherical. If it's a p orbital, it's going to be sort of like dumbbells. If it's a d orbital, well, there's a few different versions of d orbitals, and those are the types of orbitals you're going to have to draw. I am not going to have you draw f orbitals because, you know, those become a little bit too complicated to draw in just a two-dimensional picture. But there are ways of doing the s, p, and d orbitals two-dimensionally. The other thing is, if you have size and shape from the principal and angular momentum quantum numbers, the other one is the magnetic quantum number. The magnetic quantum number, m sub L, tells you the orientation of the orbital in space, okay? Now, the possible numbers of these lead you to how many different types of orbitals there are of any given type, right? So if you have an s orbital, there's only one s orbital for any given shell or principal quantum number, or any energy level. For the angular momentum quantum number, there's going to be, well, if you have, it's going to be the number of possible values for the angular momentum quantum number is dependent upon what the value of your principal quantum number is, and the value of the angular momentum quantum number will lead you to how many orbitals there are, because it leads you to the values you get from the magnetic quantum number, right? And so the table on the right shows you the possible values that you have for any of these given quantum numbers. And those quantum numbers are those solutions to the wave functions that result in the orbitals that we're about to look at. And so jumping into orbitals now. Remember, these orbitals, they are those probability distributions, right? If we were to stop a simulation or a mathematical simulation of where we would find the electrons for a hydrogen atom, right, at any given point in time, we'd get one of these dots in one of these, right? Assuming we already had our set of useful solutions for the wave function. And so we would get, if we had n was equal to 1 for a wave function and L was equal to 0, m sub L was equal to 0, we would get a 1s orbital. And so the probability distribution for the 1s orbital is what you see here, and the artist's rendering is what you see here. And if you were looking at the radial probability density, essentially what we're saying with the radial probability density is, it's the if you look at a distance from the nucleus and say, how likely am I to find an electron at a certain distance from the nucleus? You could go look at the probability density and say, okay, well, for a 1s electron, the probability of finding the electron here, say at this distance, right there, well, that's going to be this probability. And if you sum up all the probabilities for all the distances, you get a total of 1. But what you'll find is you have more probability for a 1s orbital of having the electron closer to the nucleus than if you have a 2s orbital, right? Than if you have a 3s orbital. So that's what the probability distribution is showing here. But what you do have, there are a couple key things here. You tend to have areas where there's high probability, right? So in this range, you know, out here for the 1s orbital, in this range here for the 2s, but you can see that for the 2s orbital, there's also an area down here. And for the 3s, there's an area down here, there's an area here, and there's an area here, right? And those are all high probability areas. And where you have high probability is you have something called a lobe. Okay. But you'll also notice there are areas of 0 probability. So for the 1s, you don't really see any of these. But right here, if you will, I'll try to draw a line up there. And right here for the 3s, those are areas that we call nodes. Okay. And the node is an area of low 0 probability of finding an electron. Okay, now something you'll notice about lobes and nodes. In the artist's rendering, you'll notice that, so they label where are the nodes. And in a 2s orbital, you have one node right in the middle there, between this orange area and this greenish area, right? On the 3s orbital, you have a lobe between the yellow and ish orange in the middle, the green and the green, and then between the green and the outer shell also, or the outer lobe also. And you'll notice that those are colored differently, right? So what the colors are indicating, the color indicates the phase of the wave. Right, the phase of the wave. When we say the phase of the wave, are we talking about, well, if we had a Cartesian coordinate system, just to think about this, what do we mean by phase? Are we talking about a wave that starts going up, right? Or does it start going down, if you will, right? So these two waves, right, are out of phase with each other, and in a given atomic orbital picture, different colors are separated by nodes, and those nodes separate areas of different phases. So we're just saying that the phase of the matter wave of the electron is opposite in those two areas. I'm not telling you which area starts up and which area starts down. We just know that the phase is opposite because it's an arbitrary assignment. So, yes, Maya.
Yeah, so in the book, the example of the orbital, there's not really a color change. It's just like blue and then like light blue. It doesn't have the blue and the orange.
Yeah, that would still be a color. That's still a color change.
So the little light blue line is the different color is what you're referring to?
Yeah, so there are a number of ways that these phases can be written. So it could be shaded or unshaded, which is how we're going to do it when we draw. It could be, shaded darkly, shaded lightly. It could be what some books do, and I find is problematic, is in some cases they'll put a plus or a minus sign to indicate the phase, and I don't do that for a very specific reason. It's because what happens is if you start putting pluses and minuses, people start to confuse it for charge, and we're not talking about opposite charges. We're talking about the opposite phase of the wave. Okay. So to draw these, in drawing s orbitals, we're actually going to go to the next page here because I want to make sure I have enough space to do this. So if you're drawing a 1s orbital, it's pretty simple. We'll tend to put Cartesian coordinate systems down for a variety of these things, although we don't always need the full Cartesian coordinate system. I tend to have my z-axis up. That can change depending upon if we're talking about a molecule or an atom. There's our x, there's our y. And if you're looking at drawing a 1s orbital, well, our picture of the 1s orbital here, right, is just a sphere. And so a sphere on my two-dimensional page is just going to be a circle. And since I'm looking at a 1s orbital, that's going to be a relatively small circle. Okay. Again, hard to draw these on here, but I'll do my best. Hopefully when you draw these on paper, they'll look a little bit better. If you're looking at a 2s orbital, again, we'll have a Cartesian coordinate system. Okay. Now you have to depict the two different lobes. And so what we'll do first is just draw a smaller lobe, and then around that we'll draw the bigger lobe. Okay, and so you've got the node. Oop, I missed my small one. There we go. So there's a small in the middle there where the line is. We're considering that to be where the node is. And then the outer line is just where we consider the end of our probability distribution that encompasses 99%, the electron 99% of the time. Now we have these two lobes, one here right on the outside and one in the middle, and we're just going to shade one of them and leave the other one unshaded. And that's going to depict our lobe having our lobes having opposite phases to each other. Okay. There's a tool that I can do that here. Yeah, no, okay. And so that's really what I'm looking for here. It's just shade it in as best you can. When you're drawing, you can shade it in a little bit better than I'm going to be able to do because of the limitations of this particular tool, but it's something that shouldn't be too hard. So now you have the two lobes, the shaded and unshaded, representing the two phases of the wave function in those regions. And in between, you have this line that represents the node in between those phases. And so for the 3s, we'll have our Cartesian coordinate system again. And we'll again have a small region. We'll have a region around that that's a little bit bigger. And then around that, it's even bigger still. Because remember, with this 3s orbital, the average distance from the nucleus is greater. And then we have now, again, the outer circle, right? The outer circle just says that's the end of this probability density of 99%. And then we have now two circles on the inside. Each of those circles represents a node, and we have now two lobes. And so you can do this in either way. You can either shade, and what I'll do here is I'll shade the inside. Okay, and then I'll shade the outside so that they're opposite, right? They alternate, if you will. Okay. And ideally, I could just fill this with a bigger pen, but the pen tool here is limited. Okay, and so that is now representing the different phases associated with that 3s orbital. Okay. Again, you have alternating phases, so shaded, unshaded, shaded, separated, each of the shaded and unshaded regions by a node. Okay. And that's really all there is to drawing these. Of course, if you're drawing this on paper, it's a little easier than it is trying to draw on a computer screen a lot of the time, especially when you're using a stylus. So, so that's something that hopefully as you draw things out, you'll have a better ability to do this and make it clearer. So using the pictures in the book can be important, and you know, maybe drawing better than I do, like, you know, like a kindergartner, it would help too. So if you are artistically inclined, that is really useful for you. All right, so let's start. I see two people have raised their hands. One moment. All right, so Maya.
I think Amir was before me, so you can let
Okay,
him
Amir.
ask.
Quick question, sir. You said on every level of this, say 1s, 2s, 3s, the phase of wave keeps changing from, say, positive to, not positive to negative, but going up and down.
Yeah. Mm-hmm.
And it is constant throughout how many s's we go, like how many layers we go. Why it happens?
That's coming out of the math of the wave functions. Like that's as far as I'm going to explain, right? That is actually from the wave functions and from the solution to the wave functions, having those in L M sub L values. So it comes from the calculus involved there and the operator math.
Understood. Thank you.
Mm-hmm. Maya?
I just have a shading question. So it doesn't really matter how we shade it as long as it's, quote, alternating?
Yes.
Okay.
Yeah. Yeah, it's arbitrary for what all of our intents and purposes. Okay. So that's for the 1s orbitals. Remember, for the s orbitals, just to keep in reminder, s orbitals, okay, they will all have, so an L value equal to 0, and the M sub L value will equal 0 for all of these orbitals, right? So on the 1s, n is equal to 1, on the 2s, n is equal to 2, and on the 3s, n is equal to 3, but the L value is going to be 0, and the M sub L is going to be 0. Okay. All right. So those are the s orbitals. we also have these things called p orbitals, and the p orbitals have some different values. We're just going to start out with the 2p orbitals. Those are sort of the simplest ones that we're going to look at. And so for the p orbitals, I'm actually going to put this up in the top right. The L value for p orbitals will equal 1, which means your m sub L value for any of the p orbitals will be 1, 0, or -1. Those are the possible values you have for those quantum numbers. For the 2p, the n value, of course, is 2. And so what you see here is now you've got 2 lobes, right? You got, so the lobe here, right, and a lobe here. Those 2 lobes are on an axis. And so we now have 3 different orbitals that we're describing. We know we have 3 orbitals because up here for the m sub L value, we've got -1, 0, and 1, right? -1, 0, and 1 are the values that we have for m sub L. There are 3 possible values for m sub L, which means we have 3 possible orbitals with that just with that type of the solution there, okay? And so these 3 orbitals for n is equal to 2, L is equal to 1, we have the 2px, the 2py, and the 2pz. And the 2 lobes are spherical-ish. They're not quite spherical, but they lie in a line on an axis. So if you have the 2px orbital, the lobes lie on the x-axis. If you have a 2py, the lobes lie on the y-axis, and if you have a 2pz orbital, they lie on the z-axis. So when it comes to assigning the m sub L value to any of these orbitals, it's an arbitrary assignment. So I'm not worried about you assigning and saying, oh, well, m sub L is -1 for x, m sub L is 1 for y, and m sub L is 0 for pz, the 2pz orbital. I don't care. It can be any way you want to do it as long as they have different values to it. But what you will also notice is we do have, each of these has 2 lobes, right? And those lobes are separated by what's called a nodal plane. So for the px orbital, the px orbital is oriented along the x-axis. And so there is a nodal plane that is that lies in the YZ plane, okay? And so there's no electron density in that plane, okay? And then your lobes are separated by that plane, and so the 2 lobes are gonna have different, different phases, okay? And so these are the artist renderings. I'm gonna draw not artist renderings here in a second, and I'm going to try to keep them simple. We're going to be able to draw the 2p and the 3p orbitals. And so we'll do that starting on our next page. So we'll start up here with the 2px. Now, when drawing these, I'm not expecting you to be an artist. All I really expect is you to draw me a Cartesian coordinate system. I don't even expect you to have all 3 axes. If you have a 2px Cartesian coordinate or orbital, you need to have your x-axis in the Cartesian coordinate system. So you can do x and y. And when you're doing this, sort of as chemists, over the course of time, sort of conventionally, we tend to draw our p orbitals almost like a figure 8 that goes through the origin, right? And that's not perfectly true for the actual simulation, but it's a fast way of drawing these in a reasonable way that gives you a nodal plane, right? And so the nodal plane on this particular drawing lies in the YZ axis, assuming that the Z axis is coming, if you will, out of your screen at you, okay? And so then you just have to shade in one side of it. And you know that this is the px orbital because it has this shape, and the axis on which the orbital is lying, right, is the x-axis. And then you could do the 2py, and all you'd have to do here, if we want to keep the Cartesian coordinate system in the same orientation, that's fine. As long as you have a y-axis in there, it's not a big deal, right? So I'm just going to keep my y-axis vertical and my x-axis horizontal here, and I'm going to draw the same basic shape. Okay, and shade in one of the two sides, just to note that they're opposite faces. It does not matter which side you shade in as long as one is shaded and the other is not, because that's an arbitrary assignment for the face. Okay. For me, I tend to pick the side that looks more distorted to shade in so that I can fill it in a little bit more and make it look better. And then you have the 2pz. I tend to do my 2pz orbital with my x and z axes. It doesn't really matter which one you do, as long as your orbital is lying on the z-axis. Because remember, the orientation of the Cartesian coordinate system that we draw is arbitrary just based on how we want to draw it. And so we'll shade in one of those two lobes. Again, knowing now for the xz, for the 2pz orbital, the nodal plane is the xy plane, right? For the 2py orbital, the nodal plane is the xz plane. And so that's how we would draw the 2p orbitals, right? So 2px, 2py, and 2pz. Now, when you go to the next type of an orbital.
Question, Professor.
Mm-hmm.
I know it's going to come up in an exam. So say we draw the p orbital and the z-axis. Am I saying that right?
Mm-hmm.
But we accidentally write the incorrect coordinates. Like we write yx instead of zx. That would be considered incorrect, correct?
If you're writing the 2pz orbital, the orbital density has to lie on that z-axis.
Okay, so if we were to write the y-x-axis, but write it as a z, it would be incorrect. Okay, so we have to make sure that our coordinates are like that you have right there.
Right, that essentially, if you have a z here, right, that's got to match the axis there that you have your orbital on.
Okay.
So if we have our artist picture of the 2p x, 2py, and 2pz orbitals like so, and we can draw them like that, it makes our lives a little easier, right? Drawing something in 2 dimensions is a whole heck of a lot easier than drawing it in 3, which is kind of how, if you go back up to the s orbitals, the 2-dimensional pictures of the s orbitals is also a whole heck of a lot easier to draw like this than the artist rendering that you have, say, right here in the middle. But one of the key things also is and this is where I'm kind of headed with this, is the artist here has rendered the different lobes very, very nicely. And so you have only one lobe, if you will, for the 1s orbital. For the 2s, you got one node in the middle of the 2 different regions, 2 different lobes for the 2s orbital, and then you've got 2 nodes for the 3s. So as you have a higher and higher in value, right, a higher and higher principal quantum number, you have more nodes in here. Now, as we go into the 3p, okay, so one of the things about these orbitals, remember, if for the n is equal to 1, we only have s orbitals. For n is equal to 2, we have s and p orbitals, so we have 1s. And then you have the 2px, 2py, and 2pz. For n is equal to 3, you have the 3s, the 3p, and then we'll get into the 3d orbitals. But the 3p orbitals are going to look a little bit like these 2p orbitals, except they have more nodes. And so we're going to just depict those nodes in a similar way to what we did with the 1s, 2s, and 3s orbitals. So here we'll look at the 3px, understanding that the 3px orbital is more complex than the 2px, and it's going to be overall a little bit bigger. Okay, so here's I'll do my y and x axes. What we have here is for these 3p orbitals, you wind up having 2 small regions of electron density closer to the origin. And then outside of that, you actually, on the axis still, have a bigger region, okay? So it looks something like this. I know it's not the greatest. Let me see if I can adjust my axis here. There. Okay, so this orbital is bigger than the 2px, And now when it comes to the shading of the orbitals, right, and the phases of the orbitals, again, you're alternating phases. So we have a lobe here. Okay, so one lobe there of that. And so we're going to color this one in. And then we have next to that, in between the two lobes, we have a node. Right? So there's a node there. Right, just like you had the nodal plane, right, on the 2x. Now you have more nodes on the 3px, right? Then you have, on the other side of that, you have another node, right? And then we'll shade in the next region. So you can see alternating shaded, unshaded, right? So to describe the phase of the wave function, right? And then there's another node, and the last section we'll leave as unshaded there, okay? And so that's sort of what a 3px orbital looks like, you know, with the limitations of drawing on the screen, okay? And so that's pretty much it. We do the same basic idea now for the 3py. Right, so you have the two small lobes on the inside, and then the two bigger lobes outside of those on that axis. And of course, shade them in. Appropriately. Okay. There's one. We got a node in between, and then we've got this other lobe. It'll be shaded. And so it's really as simple as drawing them like that, right? And then of course for the 3pz, we go through the same process. Right? And we just label the axes that were on the z-axis, and of course you could draw the x or y for the other one. It really wouldn't matter. And you could just alternate the shaded and unshaded regions again. And this is the point where I missed my whiteboards. All right. And so those are your 2p orbitals and your 3p orbitals, okay? And so there's one other set of orbitals. I'm only really wanting you to be able to draw all of the orbitals in the first, second, or third shells, right? First, second, or third energy level, so where n is equal to 1, 2, or 3. We don't have 4p orbitals. They don't exist. There's just not enough space around the nucleus to have electrons and orbitals in f orbitals, or excuse me, in d orbitals until you get to the third energy level, and you don't have enough space for orbitals in f orbitals until you get to the fourth energy level. And so we're going to sort of cut our drawings off at the third energy level just to make sure you sort of get the whole point is you want to know where you have regions of electron density and what is the orientation of that electron density, because that'll have implications again for bonding as we get into chapters 8 and 9. So let's go on to the next one. The next one is d orbital. So there are 5 d orbitals here, okay? Now, in a d orbital, the values you have here, L for a d orbital will equal 2. And so M sub L will equal 2, 1, 0, -1, or -2. And so there are 5 different values for d orbitals, which means you have 5 different d orbitals. Now, you'll notice that the labeling of these orbitals is a little different. You need to know how to name and draw these orbitals. So you got the 3 dxy, the 3dxz, and the 3dyz, which all look pretty similar to each other. You also have the 3dx squared minus y squared. We're going to look at the 3dxy, dxz, and dyz first. What you'll notice is in these orbitals, there's a set of lobes. You have 4 lobes that lie in a plane. Now, those lobes, they lie, if it's the 3dxy orbital, those lobes lie in this xy plane, right? If it's the 3dxz orbitals, the lobes lie in the xz plane. And if it's the 3dxz orbitals, they lie in the, dyz orbitals, they lie in the yz plane, okay? So there are actually 2 nodal planes for each of these 3 orbitals. And those nodal planes lie, well, if it's the 3dxy, the 2 nodal planes are the yz plane and the xz plane. So planes that form with the z-axis and the axis either the x or the y for the dxy. All right, so you have 2 nodal planes there, and then the orbital density lies in the plane that's described by the label of the orbital. Okay. Now, a thing about this is the electron density here is in the middle of the axes, right? So it's not on, the orbital density does not lie on the axes for the dxy, the dxz, and the dyz orbitals. However, if you look at the 3dx squared minus y squared, it essentially has the same type of shape as those other 3, except now it's still in the xy plane, right? It's still lying in the plane that's described by the name, but now the orbital densities are along the axes, and the nodal planes bisect the axes. So you have the nodal plane for the dx squared minus y squared lies between, so on the z-axis, and it bisects the x and y axes. And then you have another one that lies on the z-axis, and it bisects the x and y axes in the opposite direction. Okay. Now it'll be easy to depict these in the way that we're going to do it, because we're going to depict these 2-dimensionally. Now the other type of d orbital that's out there is the dz squared orbital, and that looks like this funky little thing, right? And this funky little thing, you can see the node depicted here in this sort of shaded thing, right? It's not a nodal plane anymore. It's almost like 2 nodal cones, if you will. And so here you have 1, 2, 3 lobes, and 2 of the lobes on the top, the one on the top and the one on the bottom, are in the same phase, and they're separated by this sort of a donut lobe that goes around the middle. And that donut lobe that goes around the middle is in the opposite phase of the other 2. And that donut lobe lies on the xy plane, whereas the other lobes lie on the z-axis, okay? So that's the artist rendering. Like I said, I'm not expecting you to draw something quite so nice. So we're gonna go and draw all of these orbitals. And as we do so, you'll see that they're really simple to draw if you draw them in just the plane on which they lie, okay? So we'll start out with the 3dxy orbital, okay? And so for this, all I really care for you to do is draw out your x and y axes. And your orbital densities will lie in each quadrant, okay? And try to get them as close to the same size as you can, right? Again, not expecting you to be an artist, but to depict these fairly simply, you would just shade in, if you were to go clockwise or counterclockwise around the origin, right? You would just shade them in alternating colors. Doesn't matter, it's arbitrary which ones, which way you go, if you go shaded, unshaded, shaded, unshaded, or the opposite of that, okay?
Professor, they're not touching. Is that okay?
That's fine, as long, so remember, I am not an artist, and I don't expect you to be an artist. If you were to have a good rendering of this, you would actually have scales that were better depicted, let's say. Okay, so I'm expecting you to have the basic understanding of the shapes and orientations, but not necessarily, it doesn't have to necessarily be perfectly drawn.
Sorry, so something like this, would it be acceptable? The reason I'm asking is I'm used to drawing it like this, and like
Hold on one
not
sec.
just circles.
One sec. Show me that again, Amir.
Here.
Yeah, that's fine. That's fine too. Yeah.
Thank you very much.
All right, so there's 3dxy. We'll do the 3dxz. So here, your axes are the z and the x-axis. Again, shaded, it just have to alternating going around the circle, just has to alternate shaded, unshaded, shaded, unshaded. Right, and you have your nodal planes are separating the lobes, and the nodal planes in these drawings are lying perpendicular to the screen because the z-axis lies perpendicular to the screen. So one of the challenging things, and I think it's going to be more challenging online, is visualizing these things in your head as you're drawing them. Remember, these are two-dimensional pictures of things that are inherently three-dimensional. So it's going to be important that you spend some time looking at images and really being able to depict them in your head. And we'll finish up here with these three orbitals with the d, y, z, and we will then go on and look at the other two. Put my z and y. Again, doesn't matter which way you label the axes, as long as they're labeled properly, right, with the correct axes, right? So you can put your y-axis up in the vertical direction and your z-axis horizontal. It doesn't really matter. I can look at those and figure that out pretty easily. Right? So shaded, unshaded, shaded, and unshaded. Okay. So all right. And so those are three of the five 3D orbitals. The other two, the 3D x squared minus y squared. Now you don't have to know why these have the labels that they have, the xy, xz, yz, x squared minus y squared, or the z squared as a subscript. Those actually come out of the math, but you don't have to know why, you just have to know what they are, right? Because that's all we're really interested in, sort of the pictorial view of these. So here we have our x and y axes again, right? Only now the orbital densities lie along, that's not very good, along the axes instead of in between them like they were before. There we go. Okay, so that's the big difference between the dx squared minus y squared and the dxy and the dxz. Okay. And then this is the hardest one to draw, and it's going to be, I'm sure it's going to be terrible. So I'll try to do my best on this. So here's the 3dz squared. All right, so I'm going to draw in all three axes for this one. Okay, I'm actually going to start out by drawing in the upper lobe here, and then sort of a little tiny circle around it, a big circle around that one. Those are meant to be lying in the XY plane. And then we have the lower part of the second lobe right there. And I'm just going to shade in right around that donut lobe in the middle. Okay. Again, not a good artist, so don't expect much. All right, so this is what I tend to think of as the DZ squared axis. Honestly, if this were on a whiteboard, it would look a little bit better, okay? But you'll notice that the two lobes, right, the top and bottom, if you will, are along the Z axis, right? And then the donut lobe is in the XY plane, okay? And so that's how you draw those, at least two-dimensionally. That's what I kind of expect you to do. And again, the whole idea is understanding where those lobes are oriented, because when it comes to bonding, that overlap of orbitals between two atoms is going to be important. In order to have overlap between two orbitals, they have to be oriented in the proper way, toward each other, essentially, such that they can overlap. All right, and so those are your 1s, 2s, 3s, the 2p and 3p orbitals, and the 3d orbitals. And those are the ones you're going to be expected to draw and understand how the quantum numbers relate to those orbitals. Okay. So when it comes to energies of orbitals, right here, so we have orbital energies that we're gonna look at just to begin with, okay? And the thing that we want to start with is we're going to start with just an understanding that the lower the energy, right, the more stable the orbital, the closer to the nucleus that orbital is, okay? When it comes to the hydrogen atom, electrons in the 1s, the 2s and the 2p, the 3s, 3p and 3d, 4s, 4p, 4d, and 4f, those are all going to be, each energy level is going to have all the orbitals that are essentially the same. Because when you talk about an electron in any of those orbitals, well, with hydrogen, you only have one electron, okay? When we start looking at multi-electron atoms in a little bit, one of the things we're going to need to see is that as we start to put electrons into an atom, okay, to build up what we call the electron configuration. Well, we're going to start with hydrogen and say, well, hydrogen has one electron. That's going to go in the lowest energy orbital for the ground state, or the most stable state. So that'll go in the 1s orbital. Now you can excite them, right? If you hit hydrogen with light, you can cause that electron to go up to a higher energy orbital. But in its most stable state, it's going to be in a lower energy, right? If it absorbs light, it'll go to a higher energy orbital. And of course, if it relaxes back down to the lower energy orbital from a higher energy orbital, it'll give off light. Now, when it comes to multi-electron atoms, there are going to be some differences because multi-electron atoms are just more complex. And so what we'll see is the orbital energies, as you get to bigger and bigger atoms with more and more orbitals, you're going to have some differences. So the 2s and the 2p orbitals will not be the same energy because you're starting to populate these orbitals with more than just one electron. And so what you'll look at here is say, well, the 1s will be at a certain energy, the 2s will be higher energy, and then the 2p will be a little bit higher than that, followed by the 3s, followed by the 3p, the 4s, the 3d, the 4p, continuing on up, the 5s, 5d, 5p, etc. Right? So as you go up, now you're talking about orbital energies that are less stable, that are higher in energy. Now the actual ordering of this, you can remember it using this little weird trick, okay? And this little weird trick is essentially if you say, okay, we're going to label all of these orbitals. So in value is going to be over here, and these are the possible orbitals over here. Okay, and so here n is equal to 1, right? N is equal to 2, n is equal to 3, n is equal to 4, 5, 6, 7, and 8, okay? And so all you'd have to do is you take and you draw this diagonal line through here, okay? And as you draw that diagonal line, you'll notice these all have arrows to them. The first one you hit is going to be the lowest energy. Then you go to the next level, right? And the first one you hit is the next lowest energy, right? So that'd be the 2s. Then you go to the next one. You draw another arrow, 2s down to the 2p. So you hit your 2s, 2p, right? 3s. Then you go to the next arrow, 3p, 4s. Right? Then you go to the next arrow, 3D, 4P, 5S. 3D, 4P, 5S. And that's how the ordering goes. So you'll notice that over here in this, I'm going to erase some of these real quick. You'll notice that the 4S orbital is lower in energy than the 3D. There's some subtleties to the math involved in this that you don't need to know how that happens, but you do need to know that the 4S and the 3D are sort of flipped, if you will, from what you might expect. Yes, Maya.
Where can we find that? Is that in the appendix or that actual picture, or do we need to memorize that? Or
well, it's in the notes that are available online, so you can use that there. That could be a good place to go.
okay, so it's not in the book. Well, it's not in the chapter.
I'm not remembering exactly if the book has this down. This is sort of a mnemonic device that that chemists have been using for a long, long time.
Okay, so just use the PowerPoint.
Yeah, you can use the PowerPoint for this. Yeah.
Okay, thank you.
Okay, so that's how you would order those energies. Okay. Now, as we start to make and put together electron configurations, we're going to use that ordering to our advantage. Okay. So before we get there, there's another thing we need to talk about, and that's this idea of electron spin and with the Pauli exclusion principle. Essentially, an electron has this magnetic moment. Okay. Now, the magnetic moment of an electron comes from, well, if you are in a physics class on electricity and magnetism, you can talk about all kinds of different ways to get magnetic fields. But basically, if you have a charge that spins or a charged particle that's spinning, it creates a magnetic field. And so there's another quantum number. This is the fourth quantum number that I alluded to yesterday. This fourth quantum number is called the electron spin quantum number. Okay, and so the electron spin quantum number has an abbreviation M sub s. Okay, and it has two possible values. Those two possible values are +1/2 and -1/2. And yeah, those are part of the solutions to the wave functions. And the +1/2 or -1/2 assignment is arbitrary, but we go by some conventions for which we assign first. And so what this is, basically, if you have a negative charge that's spinning, it creates a magnetic field. And that magnetic field allows for two electrons to fit into the same nucleus. Sorry, not nucleus, same orbital. So the electrons you can fit now two electrons into the same orbital. And we can think about it in kind of this kind of a way. If you were to put two negative charges in the space that an orbital describes, that's two negative charges that are very close together. They don't necessarily want to be that close together. And so they're going to repel each other. But that repulsion is minimized by having these magnetic fields. Right? And if you think about two magnets, right? If those two magnets are oriented with their magnetic fields in the same direction, they repel each other. But if you flip them, they attract each other, right? And so your north and south poles will attract each other. And so that allows these electrons to sit in the same orbital. So you can have two electrons in the same orbital at any given time. And so that plays with what's called the Pauli exclusion principle, which basically says, well, no two electrons can have the same set of 4 quantum numbers, okay? So 4 quantum numbers. So the set of 4 quantum numbers, okay? Okay, are, so in L, M sub L, right? And then you have M sub S, okay? And so your N, L, and M sub L describe the orbital in which the electron resides, okay? The M sub S describes the spin of that electron. So the plus 1/2 or minus 1/2 will be the spin. So if we look at the table on the right, in the 1s orbital, so n is equal to 1, L is equal to 0, M sub L equals to 0. And so you can have two possible values for M sub S, which will relay the information to you that there are 2 electrons that can sit in that orbital. For the second energy level, you have the L of 0, which is your s orbital. Your M sub L will equal 0, and you have 2 values for M sub S, which means that you have 2 possible electrons that can fit into the 2s orbital. But you also have the 2 p orbitals. Now, L is equal to 0, which means there are 1, 2, 3 possibilities for M sub L, and each of those M sub L's, right, each of those orbitals, the px, the py, and the pz, can fit 2 electrons in them. So for the second shell, you can have up to 8 electrons in the second shell. For the third shell, well, you have s, p, and d orbitals, and there are 1s orbital in the third shell. You have 3 p orbitals in the third shell, and you have 5 d orbitals in the third shell. And so that gives you a total of 9 total orbitals, which means you can fit a total of 18 electrons in the third shell. Okay. Now, a couple of ways to depict electrons, right? When we depict electrons, we've used that E with a negative exponent on it, right? We've also, so something else we can now use to depict electrons, we can use their spin, plus 1/2 or minus 1/2. Something we as chemists use is we actually use these little arrows. So you can say an arrow pointing up or an arrow pointing down. That represents, so we call that spin up or spin down. And all we're saying there is the spin of the electron creates a magnetic field that's pointing up, or the spin of an electron that creates a magnetic field that's pointing down. That's all we're saying there. Or you can also use another version is just half arrows, spin up and spin down. Those are all okay ways of depicting electrons, which will be important as we start to see how those electrons are organized within a given atom. Okay. All right, so we now have all 4 quantum numbers to describe these electrons, right? The first 3 quantum numbers describe the orbital that in which the electron resides, and the 4th quantum number describes the spin of that electron and its magnetic field that it generates when the negative charge spins. Okay, so as we start to look at other atoms, there's this thing that becomes a challenge for us. Well, it doesn't really become a challenge. It is a challenge. It's flat out. It's one of the hardest things, one of the biggest problems with the models that we're using, okay? So our model is only good for hydrogen, okay? It's only officially good for the hydrogen atom. How do we know that? Well, we do this mathematical model, and we model the orbitals, say. And that model takes into account the proton and the electron and the distances and the wave function of the electrons. And for hydrogen, it's really simple to do. You can do that, and it matches well, and this is the key, it matches well with experiment, right? So that's one of the keys. These models are meant to be tested by experiment. If your experiment agrees with the model, you've got a good model for something, okay? Now, models vary in how good they are at doing different things. But the point is, we know it's a good model for the hydrogen atom because experiments have helped us figure that out. Now, if you try to go and model other atoms, even if you go to the next simplest atom, helium. Helium, right, in a helium atom, okay, you still have a nucleus, right? The nucleus of a helium atom has 2 protons and 2 neutrons. And so that's got a +2 charge in the middle. And the magnitude of the charge isn't the problem. What happens is you now have 2 electrons. When you have 2 electrons and a nucleus, that's when you have a problem. called a three-body problem. It's basically a problem between so you've got attractions between the nucleus and the electrons, right? So there are attractions, there's an attraction between the nucleus and one electron and the nucleus and the other electron, okay? There's attractions there. However, between the two electrons, right, you have repulsions, right? And when doing this mathematical model, you're essentially modeling the three-dimensional position and movement of these particles to get energies out. And the energies that these models produce are actually, for a helium atom, they're dependent on where you start the electrons in this simulation in the first place, which is a problem because the energy of a helium atom doesn't depend on where the electrons are at when you start the helium atom, right? You would expect that as you do the simulation, you would wind up always coming to the same energy, but that's not what happens. As you do these calculations and these simulations, if you have the electrons, say, two different locations, you'll get two different energies, which means that it's not a great simulation for even the helium atom. And it gets worse and worse as you go, right? The more particles you have, the harder it is to track the energy levels of these atoms. Okay, so I've just told you now, all the stuff that we've talked about is only good for one atom. That's kind of discouraging, right? Except it's not, because what's really nice about it, remember, we're modeling something in the real world. So the whole point of this model is to make sure the model agrees with experiment. And the model that we have for the hydrogen atom actually agrees pretty well with experiments for all other atoms. And so we can take the model, these wave functions and probability distributions, these orbitals that we generate from the hydrogen atom calculations, and we can use those in our descriptions of all of the other atoms because we know that it agrees well with the experiments on those other atoms. So the hydrogen model actually is kind of extended out. Now it's not 100% perfect in every situation, but it's a very good model for us for other atoms, okay? And so as we start to now look at how the atoms other than hydrogen have their electrons distributed around the nucleus, we can use the hydrogen atom model to our advantage. Now, briefly going to talk about the history of the periodic table, and then we're about to start filling orbitals. So the periodic table has all of the elements, and we've talked about this throughout the class. They're organized in such a way that the elements with similar properties are in the same group, and in any given period, right, you periodically encounter an element with the same type of properties. So that's why they're all grouped together. They have similar properties. And the first person to do this was a guy named Dmitry Mendeleev. And this is an example of a periodic table that would look like what he had put together, where he's grouping things like hydrogen and lithium and sodium and potassium. And then you see copper in here, right? Well, copper does have a +1 ion. So does silver. So does gold. And so that's why those might be put in here. You'll notice there are not much in the way of transition metals in this. But you'll see the groupings that are really similar. Now, this has evolved since then, but the reason that this periodic table was made in this way is because of how those elements interact with other elements, their physical and chemical properties. Well, it turns out that the physical and chemical properties of the elements are largely based upon how the electrons are ordered around that nucleus. And that's why it's important that we look at the what's called the electron configurations of the various, of all of these atoms. And so we can start to see similarities between the elements and their electron configurations, okay? So, to begin with this, a lot of writing on this chart. We'll get through the writing and then we'll start to do some of these electron configurations. Okay, so what we're going to do now, we're going to look at the Aufbau principle and the periodic table, okay? So as protons are added one by one to the nucleus to build up the elements. So basically we're gonna look at the elements. We're gonna start with hydrogen. We're gonna go from hydrogen to helium, right? To lithium, to beryllium. And as we go through the periodic table, we're adding protons to the nucleus, right? And neutrons, but the protons are the thing that just define the element. And as we do that, we're also adding electrons. Now, where do those electrons go, right? We know all the protons and neutrons are in the nucleus, but the electrons are in these orbitals, okay? And so we're gonna add these electrons to the orbitals from the most stable orbital to the least stable orbital until we run out of electrons for each given atom, okay? And the orbitals that we're adding to, those are the hydrogen-like atomic orbitals, the ones that we said actually do a good job of describing these. And so when we look at elements in the same group, we're going to find that elements in the same group are going to have the same, what's called a valence electron configuration. And that's a key thing here, okay? So when we think about valence electrons, okay? Valence electrons, right? Those are important. Those are really important. Valence electrons are the electrons in the outermost principal quantum number level, okay? So the outermost shell, if you will, okay? And those are the ones that are gonna be, since they're the farthest out, they're the ones that are gonna be involved in things like bonding. They're gonna be largely the electrons that are most likely to be given off for a cation, or you could fill an orbital for an anion, okay? So that's elements in the same group, okay? Elements in the same period have the same core electron configuration, okay? The core electrons and so we'll highlight sort of the definition of core electrons. So the core electrons, those are all in the electrons in the shells that are inside of the valence shell, right? So they're inside, they're the inner electrons that aren't included in that outer shell, okay? And the electron configuration of the core is going to be the same as the electron configuration of the noble gas in the period above, okay? And so that's something we'll start to see as we do electron configurations and abbreviated electron configurations, okay? Now, there's one other rule here that we need in order to do this, and that's Hund's rule. Hund's rule tells us that as we fill orbitals with electrons, okay, what we're gonna do, right? We start putting these electrons in the lowest energy orbitals, start filling to the higher energy. And as we do that, well, we might encounter orbitals that are the same energy, okay? For example, if we go back up to our hierarchy of orbitals, well, for the 1s orbital, there's only one of those, right? For the 2s, there's only one of the 2s orbitals. But for the 2p, right, the 2p orbitals, right, there are 3 orbitals here. And those orbitals are all the same energy, right? For the 3s, you have 1 orbital. For the 3p, you have 3 orbitals, right? If you look at the 3d, though, there are 5 orbitals, okay? And so those orbitals, each group, right, the 3p orbitals have 3 orbitals that are the same energy. Those are called degenerate energy. They're the same energy. And so as we fill orbitals with electrons, when we encounter a situation in which the next electron that we're going to place is going to be placed in an orbital, or it can be either placed in an orbital that's of the same energy. If I have 3 orbitals that are the same energy, and let's say I have 1 orbital in one of them, well, I can put, I have choices for where I'm going to put the next electron. So we'll start to see that as we get to the second period. So we're going to start out putting these together for the first period, go to the second period, and really start to fill in all of the electron configurations for the various atoms. So we're starting with hydrogen, okay? So we're gonna come here to the element, start with hydrogen. It has 1 electron. That 1 electron goes in the lowest energy orbital, okay? So we have from the slide above that the lowest energy orbital is the 1s orbital. And so we're going to write that 1s orbital and put how many electrons are in that 1s orbital. There's 1 electron in that 1s orbital. We can also, and so that's the electron configuration of hydrogen in its ground state. Okay, that's a key here. Most stable state. If we look at what's called a box diagram depicts the orbitals as a box. And so we're going to label the box for that orbital, just a different way of depicting the electron configuration. And inside that box, I'm going to draw an arrow representing an electron. So this shows there's 1 electron in the 1s orbital for a hydrogen atom, okay? For the abbreviated electron configuration of the hydrogen atom, don't worry about that, okay? We don't need to do that right now. That's stuff you don't actually have for hydrogen, okay? And then we can go on to our next element, helium. That did not look like an H. Nope. There we go. So helium has 2 electrons. Now those 2 electrons are going to go in the same orbital because we can fit 2 electrons per orbital, and we don't have to start putting electrons into a higher energy orbital until we fill up all of the ones of the same energy. So here I can put both of those electrons into the 1s orbital. So we go to our box diagram, 1s with 2 electrons in it. And again, we do not need the abbreviated box diagram for this. Our next element, okay, is lithium, which has 3 electrons. And so its electron configuration, well, we're going to fill up the 1s orbital with 2 electrons. And then if we go back up to the next orbital, right, we fill up the 1s orbital. Now we go to the 2s orbital. Okay, and so we're going to go back to that, and we're going to put the next electron into the 2s orbital. So here we say 2s. Well, we've used 2 of the 3 electrons, so there's only 1 remaining. So that'll be a 2s1. And so here we have our 1s orbital and our 2s orbital. In the 1s orbital, we have 2 electrons, and in our 2s, we have 1 electron. Now, this is where we can actually do the abbreviated electron configuration. In the abbreviated electron configuration, we represent the core electrons by the noble gas written in brackets. The noble gas is the noble gas of the row above, so that would be helium for lithium. And so you'll notice, I'll change my color here so I don't mix it up too much. You'll notice that the electron configuration of helium, right, circled in blue there, is the same as the core electron configuration, right? And so for core electrons, right, I'm just circling that in blue there. And then to depict the valence electrons, so the valence electrons here will be in green, right? Oops. Okay, and so when you have the abbreviated electron configuration for lithium, the core electrons are depicted in brackets around the noble gas of the row above, the helium, and then you just write in the valence that's not good. Then you just write in the valence electrons. So you have the 2s, and there's 1 electron in that orbital. So if we go to beryllium now, there are 4 electrons in beryllium. The first 2 go into the 1s orbital, and the next 2 go into the 2s orbital. And so we start filling them up in the box diagram. Oop, that's not right. All right, so we go 1s and 2s, and we go 1, 2 in the 1s, and 1, 2 in the 2s. And so our abbreviated electron configuration, we'll do the abbreviated electron diagrams here in a second, is again, helium is the core electrons. And now you have the valence electrons are 2s 2. Okay, so we can do this the same way for an abbreviated box diagram. So we're really just depicting primarily the valence electrons because those are the important ones. So we'll go back up to lithium. Helium is in brackets because that's our core. And then we can draw in a box labeled 2s and put 1 electron in there. For beryllium, again, the core is helium, and we make a box with the 2s orbital with 2 electrons in it, okay? And so what we're gonna wind up doing, so what we'll do tomorrow is we'll go through the first set of elements, at least until we get tired of doing this, and we'll fill those in, and then we'll talk about some atomic properties. It shouldn't take super long to do it. I'm going to go through it fairly quickly, and I might not go through all of them, but we'll talk about some key things tomorrow for filling these the orbitals with electrons. Okay, and then we'll go and be able to work on the lab, which is the atomic model of the hydrogen atom. Okay, and so for today, that'll be it. And we'll talk more tomorrow about this stuff.